Welcome. In this lecture, I'm going to introduce Congruence Mod M, which is going to be very important in defining, well, it's important in many settings. It's important here in defining Z mod MZ, which is going to be a great example of a ring. It's also going to be very important as it's something that we're going to generalize. Okay, so we're going to start out by supposing that we have. So suppose, so we're going to have that M is going to be a natural number, so M is in the natural numbers, and we have that A and B are integers, so, and I have specific colors I want to use for those, so I can be consistent, so this is going to be A and B are going to be integers. Okay, so then what are we going to have? So by definition, we're going to have that A is congruent to B mod M, so is congruent to B modulo M. Okay, so this is what we're defining. So A is congruent to B modulo M. Okay, and this is denoted. So denoted, the way that we denote it was we write A is congruent to, so we go A is congruent to B mod M. Okay, so what does this mean? So this means this happens if and only if we have that, so if and only if M is going to divide, and we could write this in more than one way, so M is going to divide B minus A. Right, which can equivalently, so, right, it has the exact same meaning as, so equivalently, we have that M divides A minus B. Right? Because saying that these just differ by a sign, and if M divides B minus A, then it divides A minus B. Okay, great. So now, let's just kind of, I think the other thing I wanted to point out, before we go any further, I want to point out this here, we have shorthand for this. So the shorthand is mod, which you kind of see showing up there. And you'll hear people saying it. They'll say, this is, this mod this. Okay. It's very, very common shorthand. So let's kind of like process the definition. So processing the definition. Okay, so here's the first part of it, which is that, so we know that A is congruent to B mod M, so is congruent to B mod M, that this is going to, so this is going to happen if and only if we have that, so just kind of breaking things up by the definition, so this is going to happen if and only if B minus A is a multiple of M, right? And this happens if and only if, right, there exists some K, so if and only if there exists a K in the integers, so that we're going to have that B minus A is going to equal Km. Okay, and then there's yet another way to kind of write this, which is that, so there's a few more ways to write this, so we could also write that b minus a, so this is like b minus a, is contained in MZ, I'm in Canada, I can do that. We believe in me. Okay. Which is, so what is this here? So there's this here is probably new notation for you. So what do I mean when I write this? I just mean the set of all mk such that k is an integer. Okay, so this is like a whole bunch of different ways of saying the same thing. This is the definition, right? But then this is the definition of what it means to be a multiple, which is, and then this is just another way of writing this, where this is this new notation that we're going to be generalizing, so it's good to get the hang of, which is just the set of all multiples of m, or integer multiples of m. Okay, this is actually, so one of the reasons why it's actually good to kind of break it apart like this is to realize that this is actually an existence definition. So this is an existence definition. Okay, so proving that it's satisfied requires, right? So how would you show that this is satisfied, right? We're going to show that there exists this k, so you're going to have to stay with this k is and show that it works. Okay, so proving it's satisfied requires right? What do we have to do? We have to finding the k, right, and showing it works. Okay, so proving it's satisfied requires this. That should be an S. So requires finding the k and showing it works, right? And then the other part of that is that if it's satisfied, you know that the k exists, right? So if it's an existence definition, it means to prove that it's satisfied, you need to actually find the thing, right, and show that it works. That's because it's an existence proof. But if you know that it's satisfied, then you actually know that that k exists, and you can use that in your various proofs, right? And if it's satisfied, we know that the k in the integers exists. Okay? Great. And then one of the things that's going to happen is that, and this will kind of come down the line, and so I'm not going to write this, I'm just going to kind of talk about it, which is that we're going to show that this actually defines an equivalence relation. Okay? So that you can think of congruence mod M as actually, say, you know, thinking of things as being the same from the perspective of M. And so this is a notion of same, but we'll get to that down the line. Okay, so there's a lot of different parts to this definition, and what we talked about. One of the most important things is actually this kind of translation, right? Which is that what does this actually mean? Pretty much in any setting, you're going to want to go through the whole translation to think of it in all the different ways that you can think of it, because they give you kind of concrete things that you can work with when you're writing proofs. Okay, so I hope that made some sense and was helpful, and I'll see you in the next lecture.